labs, maybe you'll find CUDA. So you should, at least you should understand how you use it, okay? And so these steps are the steps that you follow in CUDA programming, and we say that the most important thing is kernel. So always you need to focus on kernel to deal with any competition problems. And here we didn't give you a specific competition problem because there are many competition problems, and always we have to think about the algorithms that let us to do that competition problems, okay? Because there is algorithm for everything, okay? There is algorithm for matrix multiplication. There is algorithm to solve linear systems. There is algorithm for numerical analysis to solve or to uh, specific, integral equations or optimization problems. There is algorithm for sorting and for indexing and so on. So we didn't focus on that. What we focus on this, how to use that in scalable computing architectures like shared memory, CUDA programming, and also distributed memory. Okay, but at least you will have the general idea about how to use this kind of programming. And also um, uh, we say that it is like in CUDA programming specifically. In CUDA programming specifically, you do everything in parallel. So it's very important to understand the architectures of CUDA programming and how to use it as well, okay? Because it's something that uh, so you will make you will develop the kernel is just a function, right? And in the function you will define your problem, computation problems. And after that, when you come and configure the kernel, always you may think about um, you have to make what we call it grid. Okay, and inside the grid there will be blocks, and blocks that mean grid. The dimensionality of grids will be like this y-axis and this x-axis. And also there is y-axis. I don't know how to draw y-axis here. Z-axis, but also can be 3-dimensional as well. That means the blocks inside the grid can be organized in 1-dimension or 2-dimension or 3-dimension as well. And this is good, this like it gives you flexibility to do a lot of computing in this way. So now assume this like this 2-dimension. So inside the grid, we will have the blocks. Blocks can be in 1-dimension. So just we have x-axis. That means how many blocks horizontally, or can be 2-dimension. How many blocks can be horizontally, and how many blocks can be vertical. Okay, so inside it we'll have blocks. Also, this is something that you configure based on your competition problem. You can make, for example, this 3 by 2. Okay, this 3 by 2 because it's 2-dimension. I'm sorry, actually, I didn't draw them in very good manner. But anyway, this 3 by 2, 3 by 2. Okay, grid. And inside the block, we will have again the threads. And the thread themselves can be 2-dimension, can be a 1-dimension, 2-dimension, or 3-dimension. Okay. and so on. Again, it will be like y-axis and x-axis. It will be the same thing. And also will be z-axis. And you can organize this depending on what you need. Okay. But there is really very good information that you should know now. I didn't say it before. If you ask me what is the maximum thread um, inside the blocks, it depends on the GPU, okay? But the older one, it has 512 thread that you can create in a single block. But now most of the GPUs, you can create 1024. 1024. So the maximum number here inside the block will be 1024, and you can organize them in different in one dimension or two dimension or three dimension. For example, if you want a block to be like 4, 1, 1. Okay, that means it will be one dimensional, and all of them 1024 and so on. So when you multiply x, because this represent x and this represent y and this represent z, if you multiply them, the total number is supposed to be 1024. If you want to define two dimension, it can be 32, for example, 32. I think if you multiply this, the total will be 1024. So you cannot go beyond these numbers, and you can check the specification of the GPU, because now there are GPUs in the market, and CUDA version that may go beyond this. But as far as I know, still you can use this based on the current code. You can use 1024. Then you can divide them, in any shape. So this is the general architecture that you want to know. You as programmer, there is really very important information that you need to know, because once you configure your kernel, you still are talking about how to configure your kernel, because kernel is the function that will be executed in any single of these threads, okay, simultaneously. It is the same program, but it will be executed in this. So we expect here we have different data. So why we call it a single program or single instruction, multiple data. Single program, that means single kernel, and the data in each of these kernel, it will be different, because it cannot be it can be still can be the same, but the idea is you have matrix, or you have a vector, and then you split it into a small unit, and then you need that program to work on each of these junk. So this is the general idea about that. So kernel, that means the GPU is single program or single instructions are multiple data. So that can be multiple data. So this is a general architecture, and what is really very important that you should understand and know how to index each one, because you need to organize this in a specific way that you can give ID for each of this one. And last time we talked how to create these IDs. You can come up with formula because you cannot hard code it. You cannot hard code them, but you can create it very easy to create to come out with I gave you some formulas to identify the ID of each thread, because these IDs of each thread can be like index for a vector, for example, can be index for matrix, can be index. You can use them for in different purposes. Okay. So this is the idea about general. Once you architectures this is the general architecture of that. So today we'll talk about when you're understanding this, and also you understand how to get the ID for each of thread, and how to organize this in different shapes. That means you understand how to use this programming. So um, today, this is an example of parallel loop. And in serial program, we use for loop, for example, to if you have a vectors or one dimension array, and we need to sum it, right? So in this case, we have to use for loop with any loop that can um, move from element to element and add it to a variable, some variable, right? So just like it is sequential. It must be sequential. Why? Because it is for loop. And this for loop, which will be incremented by one, and one is index maybe from 0 to n minus 1, and each time it will add the element. So if you have a very long vector or very long one dimension array, say actually million or billion, that it may take a long time. So in this case, if we need to parallelize this in CUDA programming, we can organize um, the GPU's thread into like one dimension, because now we are dealing with vectors, one dimension, and then we will get the idea of each thread as this can take an element. So we don't need to use the for loop in this case, but instead of that, we store the element in each of these thread, and then we sum the vector without need to loop to be sequentially. Okay, so instead of that, because all of this will be in parallel, so all of them they will be added to the global to the global variable, which is sum, without the need of looping. Okay. And this example that we're going to give you here, okay, so this the code I'm going to so B9, for example, just to see how this look like. This is a kernel. If you see, there is no loop here, but what this kernel does, and here we have only 10. We define the size of this vector array or vector is only 10 elements. But this can be like large number. And this is our kernel, because this is the kernel that it will be executed in all threads. It will be the same, but it will be in different data. And if you see here, what we do, the argument is array. The argument, the parameters is an array pointers. Then we use this pointer to add um, uh, this will be global for all of them. This will be global for all of them. Why? Because it's a parameter that we will get from outside. Okay. So once we get this parameter, once we get these pointers, so each thread will identify the ID. It's the IDs. Okay, so just like it's the index, and then it will use its index. It will be like the array here. So it's gonna add the elements. Okay, so it's just like summing. And if you see here, we are adding this without using any for loop. All we use just if statement, because we need to control that if n, as long as n less than the ID less than n, okay, that means it will be ID. Then we need to, we need to multiply this matrix multiplication, okay, array multiplication. So we get this, okay, and then when we move because that is the kernel, then anything else should be the same in almost all CUDA programs. Okay, so we will do the same steps. Okay, so now here we have the array. We declare the array, right? And we give n. Why it is, we can begin with like h because this should be in the host, right? As we learn. If it is begin with h, it will be good practice, but unfortunately it's just array. It's okay, but it should begin with h because we know that this array, it will be on the host or in the CPU. And again, we declare another pointer, but this pointer we need to later on we will allocate this variable on the device or in the GPU memory. And then we populate. And when we initialize the array like that, for example, we find an element because here this is just like fast way to populate our array. But if you have your own array, of course, it should be here. But here, just we need to simulate some data, and we need to populate this with some data. So each element will be the index. Okay, it should be from 0 to n, from 0 to 9, and each element will be populated by the index of. It's simple like that, but it can be in array. Okay, it's just for demonstration. After that, everything is very familiar to you because those are the steps that we follow in most of the CUDA programming standard. We have to allocate memory on the device, and then we have to copy data from the host device. Also, we'll use this function, and then we will launch the kernel. And if you see the kernel configuration here, this is the dimension. That means it1. This is for grid. So we have a single grid, one-dimensional grid. And n, so this is the number of elements because it is just a vector, right? So it is like, so in this case, by configuring this, we mean that it's just like, our grid will be like this, and this will be element until n element. Okay, so because one dimension. Okay, and so once we execute this will be executed on all thread. If you go back to the thread, so it's going to take again where we will launch the kernel. We provided with device array. Okay, because the computation will take place on the kernel, and if you go back to the kernel, it will take this. Okay, so array IDX, it will multiply it. Okay, so like each element would be multiplied by itself by the same number. So this is just like it multiplies the element by itself, and it will store it also on the array. Okay, so after that, everything is familiar because already we did this. Then CUDA, then we have to copy. We have to copy the result from the device to the host. So once we get in the host, then we can print it. So this is just a serial or sequential program to print an array already we copied from the device. Okay, and at the end we need to deallocate any allocate memory on the device because we need to free the image. So when we run this, It says in CC. Okay, so if you see 1, 4, 9, 16, 25, so we multiplied each element by itself. Okay, so this is the idea behind that. The idea is, the example is very simple, but the idea to show you how to use for loop. Here we didn't use any for loop. We didn't use any for loop. You can use that, you can do this sequential, of course, by using for loop, but instead of for loop, here we benefit from the configuration of the thread, and then with the thread ID, and each thread represent an element for the vectors. Okay, so this one of uh, just to show you how to use thread ID very efficiently, and also how to figure out to get that ID. Uh, if we talk about memory management system, so we say that there is the host and device relationship. Most of the sequential work will be on the host, on the CPU. If you have data also, we have to allocate that depend on how data is large. If it is really very large, we can allocate a specific um, area in the memory of the host or of the GPU, and then we move or transfer that copy that data from the host to the GPU. But there is something that we should understand when we are working with a RAM or random access memory of the CPU or the host. The operating system, if you allocate any data on the CPU memory, so the operating system split will split that into a specific block. So we call that batches. Okay, so this one off. And the reason why, because to prepare this, especially if you are dealing with very large data, okay? So batching is very important techniques to manage the memory of the host or of the CPU. The reason why, because if you have like data more than the capacity of the RAM or the random access memory already you have, then part of this batches will be removed to the swap. Okay, so when you are working with memory, you have physical memory and virtual memory. The physical memory is the actual memory that you have, RAM, okay, like in gigabytes. And virtual memory, that is a part of the hard drive or hard disk storage system, um, will be used as memory. So it will be like extension for memory. In the CPU, that is fine. That's some kind of management, and really is very good and very efficient if you are doing any programming in a CPU. That is fine, because, but always you need to think about the communication between the memory, and between the hard drive. The bandwidth will not be that fast. Okay, the communication, there is communication, of course, but the communication will not be very fast. Okay, because of this vision. And so for the GPU, if we need to copy, when we allocate memory, when we allocate, for example, like we have a matrix, we allocated the memory on the CPU, then the operating system will create pages for that. And if it's very large, also it will swap it. Part of it will store it on the physical memory, and part of it will store it in virtual memory, like swap. The GPU doesn't like that, okay? So it will really, it will have some kind of problem to access the pageable, they call it pageable memory. So in this case, it will create what we call it pinned memory. So once we get from the pageable memory, it will do pinned memory. That means also it will create like encapsulate. So it's the data that it will we need to copy it from the host to the GPU device. It will be created in a pin. That means it cannot be moved to the swap. All of it must be in the memory area. Okay, so we call this pin memory. That means all of it will be in the same place. And after that, it will be removed. It will be transferred to the allocated memory on the device. As this here, we show you that. So we have allocated memory on the GPU, and this will be pageable. That means it consists of different pages, and unfortunately, some of these pages, especially if the data is very large, some of these pages will be on the swap. Like this, it cannot move to DRAM of dynamic random access memory of the device unless it converted first to pin memory. So after that, will be removed to this. Understanding this really is very important. And in the future, if you want to read more about the GPUs, also you can focus on how, especially if you are dealing with very big data. Okay, and by default, it will create some kind of pin memory, but also you can control this as well. You can control this area by some coding. Unfortunately, we are not going to cover this because the time frame of this units. But in the future, also, if you want to control this part, there are some code you can control how to allocate memory for pin memory and so on. Okay, but this is something that you should understand how. So now we will come to the CUDA memory model. This is something that also which will help you, it will help you in computing because we discussed before the shared memory architecture, and we said that the shared memory architecture is just like cores, but they have shared memory. All of them, they share memory, and there are two kind of shared memory architectures. Some of them in uniform and some of them non-uniform memory access, right? Depend on the architecture. But also they are the core or different processors, but all of them, they share memory. And in that kind of memory, we will expect what we call it race conditions and so on. Some kind of conflict may be on. So you need to protect the shared memory using a specific code and so on. So your question may be, okay, so what is the difference between CUDA, because CUDA also they use kind of shared memory. And what's the difference between CUDA architectures and shared memory architecture? So the answer is right here. Okay. We say that we have threads. This is the smallest unit in the GPU. After that, the threads are distributed into blocks. So the block is the second level of the hierarchy. And finally, we'll find the grid. Also, we have memory in on the same hierarchy. Let's start from the thread. For example, in the thread, we have registers and local memories. In register, this is the fastest memory. Okay, so when you declare, kernel is just a function, right? Like any function. You can declare any variable inside the function, right? Inside the kernel. When you declare it, if it is just a variable like int x or int y equal to 10, this very small amount, it doesn't need for very large space. So this will be stored in the registers. Okay. But what if you create an array, for example, inside the kernel? So that kernel is not, the array will not fit on the register because this is very small space of memory. Okay. So that it will be stored in local, the second level of the local memory. But because it's still if you declare anything inside the kernel variable, so that will be locally. The scope will be on that thread only. It cannot be accessed by the others. Okay, cannot be accessed by the other thread. So why we call this? I want you to understand that in each thread there is registers for normal variables, and local memory. Also, you can store arrays or anything in there. And any you declare if you declare any variable or an array inside the kernel, it will be local. It will be stored in the local memory. It cannot be accessed by others. Okay, and the lifetime, once the thread ends, the data will be destroyed. The second level is block memory, and we call this shared memory. So now we have local memory, and here we have shared memory, because inside the block we will find multiple threads. So all threads will share this memory. So once we say shared memory, immediately we have to think about, oh, there might be some kind of competitions on race condition. It might arise, right? So in this case, whenever we need to use shared memory in the flow, then you need to use synchronization technique to synchronize computing in different threads. So the shared memory will be shared by threads inside the block in a single block, but not by, you may have several blocks, right? Maybe that depend on how many blocks you have, but each block have their own shared memory, and that memory will be shared by only the thread inside that block. Okay, so this is the second level. Also, you need to understand it. And by the way, all these knowledge, you can use it when you are using computing, because sometimes you need some kind of computing to be only in thread level, and sometimes you need to gather that effort of different thread in shared memory. Also, you can use that. And the final one, and the lifetime, once block ends, it will end. It will be destroyed. The final level is global memory. And this global memory, this will be accessed by all threads inside the grids in different blocks. So this will be accessible for any thread in the grid. Okay. So every threads in all grids have access to global memories, and so always when you are programming, just be very flexible and use your logic to build your program and so on. So the lifetime of this, if you can, because most of the time you allocate a specific region of the memory in the GPU, you can destroy it. Otherwise, if you exit main, if it ended its work, also will be destroyed as well. Okay. So those serial levels, unfortunately, we're not going to cover them because of the time frame. But really, if you want to do any, in CUDA program, you need to think about this and how to use these three kind of memory very efficiently to do your computing problem. So here we go example. this is something already we discussed about registered and local memory, but we will give you examples. Variable declared in, we say that any variable declared in a kernel are stored in registers. Okay. Arrays declared in a kernel also, they are stored in the local memory. Okay. We says that. And thread local memory is used for storing variable and array specific to each thread. Also, it says that because it is just local, it is unshareable. Okay. So we'll move to this example. And so in this example, we have again we have like uh, n 256. This is the number of element. Then we have our kernel here. Always begin with underscore global underscore void, and this is the kernel name. And parameters, we have two. We have input and output. So here we use shared. Once it is shared, that means it will be shared. It will be stored in it will be stored in the block. Okay, so this will be shared. It will be shared among all thread inside that block. Okay. Then we will do some computation, computing here, partials, and the idea is just again, it will do this because to to sum an array. Okay. Then everything should be very normal because we don't need to spend some time on this. Here we allocate. We declare some variables. Some of them, whenever they start with H, that means on the host. D, that means for the device, and then we allocate memory. Then we initialize the vectors, and then we allocate memory on the device because we use CUDA malloc. And if you notice that sometimes we can allocate um, in on the host on that depend on your the size of your data. So sometimes you can allocate region, memory on the host, or sometimes just you can declare variable like this. But here we declare, already we declare pointers, and we populate them here. That's okay. And then everything will follow the same step until we get the sum. We print the sum. So in VCC. Okay, we get the sum that fast. And it is, we are doing this in parallel. The total size is 256. It can be any numbers, but we didn't use any for loop for this, for this. In fact, we split it into a small element, and after that, we add this element together. And the idea is just to show um, uh, how to use this shared. Whenever shared, that means it should be shared by all thread in the same in the same in the same block. Okay, so now we're going to move to memory model shared. Yeah, this already we discussed. We will not go discuss this again because if you use the keyword underscore shared and underscore, that means this will be on variable that it will be shared among all, will be shared by all thread in the block. Okay, in that block. So again, this synchronization, we need to, once we have like shared memories, then we have to speak about the about synchronization. And in CUDA programming, there are two synchronization, because we say that synchronization is really always an issue when you are dealing with parallel system. And we discuss that in other architectures. And also we're going to discuss it on distributed memory architecture as well. And here, if you have like system level, and we use this from day one, we use this CUDA device synchronize, because if we didn't use this, then the thread, the main function of the C may end before the thread finish their job. But when we use this, and just if you go back and review our old program from the first program that I gave you, welcome or hello, CUDA, you will find this. And this means that this will block the main program to stop, to not to finalize its execution, but to wait until it makes sure that all thread finish their job, and after that it can end. Okay, so this already we use this one, but for block level, because block level they have shared memory. That in this case it is very simple. Just we need to use this. If you use this keyword underscore sync threads, this it will synchronize it. Will synchronize. It will allow. It will wait before it destroy everything in the memory. It will wait. It will wait for all thread to finish their job, and after that they will continue. Okay, so they will use this specifically, and here we have this code. So yeah, so if you see this is the same thing, but here we use this keyword, and this keyword that means will allow all to wait. Okay, to wait for and after that they continue. Okay, and VCCC. Okay, so yeah, I mean, just a calculation. I think the idea is become very clear, because I want to finalize this. So now we have two examples I want to discuss, and I'm going to show you that we have vector addition. Then you can you can extend it to vector multiplication, to dot product, to anything, Uh, and also we have matrix multiplication as well. So yeah, we have 5 minutes. So let's go to B12. Okay, so this is like two vectors. As usual, we have to, they must be in a pointer. So we have A and B, and the result will be in C. Okay, and if you see here, we didn't use any for loop. Okay, because it's just like vector multiplication, and then everything is as we explained before. It's everything as it is, same step, and also the same step that I asked you maybe in the exam as well. So MVC. See, yeah, so the result. See how fast that will be because this is not sequential. This in parallel. This is like parallel. Let's go to another example. I believe P12. Is it maybe B13? Okay. Again, this for we have two metrics, and maybe you face something like that. You have like metrics, you want to multiply them, two matrices, you want to multiply them, so you can this is a technique how to do that, the kernel. And by the way, for matrix, for matrix multiplication, there are different algorithms for that. You can follow any algorithm, but this algorithm is very simple. It's not like a serial one. Um, you have to provide the matrix A and B, the two matrices that you want to multiply, and then the result will be in matrix C. Just step just for matrix multiplication, nothing fancy here. And anything else is the same. But if you go here to kernel configuration, if you see that here we multiply 32 by 32, this is a plot. And by the way, it is very good way for the grid because for kernel configuration we have to decide how many the block size, right? The dimension, like how many threads in a block and how they organize. Are they in one dimension, two dimension, or three dimension, or so on? But it is very good idea for grid size or dimension. We will try to hard code it. That means we don't need. It's not good. It's not good idea to write a number here, but you can calculate that from the dimension. From this dimension, you can calculate the dimension of the X. For example, this here for two dimension grid, X and Y. So you can compute them using this formula. And then you configure your grid using the kernel, grid X and grid Y. Look, to configure the grid size, okay? And then you feed this to the kernel and launch the kernel. Everything is normal. This part will be executed in OR thread, and it will be copied back to CPU. So now we can print them and now see how many we have. Okay, we have 100 and 100 multiplication. So let's just scale this, like for example, to 10 to be visible, to be in VCC, because it's matrix multiplication, right? So see how fast it is. And so if you can put any number, we populate them. We populate the figures here, by the way. But of course you have your own data. You can import it from file as well. But once you do that, you do matrix multiplication, and it will be parallel, so it's not sequential. So this is a lot of things. So this is the difference between yeah. So this is like two examples on how to and because this is the last lecture on CUDA GPU, now you have very good base for understanding CUDA programming. So you know the architecture of GPUs and also the work the flow of the programs, and you understand some terminology as well, and now you understand what the kernel is and how you can what's the difference between kernel and normal functions and how to configure the kernel. And this is the most important part because this based on your computational problem that you need to solve it. And by the way, you can use really CUDA for many to solve many problems. So why now in deep learning specifically, they're using CUDA and tensor like Torch, for example, and TensorFlow, and they are using CUDA programming for this because they has the capability to handle massive uh, computing problems, at the same time simultaneously, and that most of the time maybe not possible if you use CPU. Okay, so very small device, just like cell phone device, but that it has many cores, processors, and it has ability to do that um, computation for you. So this is just like, base, but you understand now, idea about this. And next time we'll talk about different architecture, which is shared memory architectures.